The investigation on fast nanosecond processes in a vacuum discharge, we began in Tomsk nearly 20 years ago. We reported the result of our work on the previous symposium on discharges and electrical insulation in vacuum. A principal result of this investigation was the establishment of the fact that the explosive processes on the cathode are of fundamental importance. These explosions occur because of a high energy density in the cathode microvolume. This high energy density is achieved due to flowing the field emission current from microphones available on the cathode. After the explosion, the intense electron emission occurs, which we call the explosive emission. The cathode area which emits the explosive emission electrons is called the emission side. At the same time, with electron emission, a plasma of the cathode metal forms on the cathode. For experiments, we use generators of high voltage nanosecond pulses with coaxial lines, resistance about 50 ohms. The leading edge was not more than 1 nanosecond in all experiments. We consider now the basic characteristics of the vacuum discharge. At the beginning, we studied current, oscillograms, and optical characteristics of the vacuum breakdown between plane electrodes. First slide, please. Picture 1 is oscillogram or voltage oscillogram, and picture 2. Picture 2 is oscillogram of current and X-ray radiation and pulse of X-ray radiation. T sub D is time lag of vacuum discharge. T sub C is time commutation. And it is X-ray, this is time. After a time lag, a pulse of X-ray radiation appears as shown in this slide. The duration of an X-ray pulse is equal to the commutation time. The next slide demonstrates, next slide please. The next slide demonstrates that the time lag shortens to a great extent with an increase in electric field. It's time lag and breakdown time lag as a function of electric field strength, molybdenum, aluminum, and plumbum. The commutation time length is directly proportional to the gap. Next slide, please. Time commutation and gap and 3 materials. These times is weakly depend on the applied voltage and the current amplitude. After a time lag, a cathode flare appears on the cathode. Later on the anode occur an anode flare as shown next slide. Next slide, please. Cathode, anode at current, anode flare, cathode flare, current. For more than 20 metals examined, the gap to commutation time ratio is order million centimeter per second, and the rate of current rise is about 10 milliard amperes per second. Next slide, please. Experimental data for the gap of about 1 millimeter. The ratio gap and time commutation 1 million centimeter per second, and rise of current and electric field and mass removal. And during the discharge, the electrodes erode. The rate of mass removal from the plane cathode for the commutation time is of order 10 up to 100 micrograms per column. And mass removal from anode and mass removal from cathode. The discharge current, anode and cathode flare, erosion, X-ray radiation, and cathode plasma velocity are identical both for the pulse breakdown and for the DC breakdown. This suggests that a spark stage of the vacuum discharge has the same nature for both the pulse and the DC cases. Let us consider an explosion of a point on the cathode. If the point is in the shape of a cylinder, the dependence for the specific energy epsilon, next slide please, on the cathode during the Joule heating can be factored as follows. Oh, sorry. It is dependence between lag time and electric field, and this slide show influence superconductivity for niobium cathode. And you can see that electric field for superconductivity cathode more than usual cathode. It is 30 degrees Kelvin. Next slide, please. If the point is a shape of a cylinder, the dependence for the specific energy epsilon on the cathode during the Joule heating can be factored as follows. G current density epsilon, specific energy, mass density, and kappa resistivity. This formula for not more than 1 nanosecond after explosive. In this relationship, we ignore the phase state of the cathode. It can be solid, liquid, vapors, or plasmatic. To evaluate the discharge time lag, one can assume that the point in the condensed phase should be heated up to a definite temperature. Then the equation, next slide please. Cathode explosion area for a pulse voltage, for a DC voltage. It is Fowler-Donaghy formula. From this criterion, one can find the dependence of the time lag on the electric field. For the DC breakdown, the criterion of the initiation of explosion will be DC breakdown and power breakdown. Next slide, please. This slide shows the dependence between lag time and current density and electric field. Dependence of explosion time lag on current density and electric field strength. Next slide, please. I wish to note else that because of the greatly nonlinear dependence of the current density G on the electric field, the rate of current density rise is very high. The next slide shows this effect. Oh, sorry. Before, no? Oh, what is it? It is electric field, it's pulse. The front of 1 nanosecond, and it is front of current density. If front of electric field 1 nanosecond, front of current density not more 10 to the minus 10 power second. It is a nonlinear effect of Fowler-Donaghy. Now we consider briefly the question on the cathode. Next slide, please. On the cathode flare plasma. The expansion velocity of this plasma is of order 1 million centimeter per second. Typically, plasma contains singly, doubly, and even triply ionized metal atoms. These ions occur at the same time with the beginning of current rise for about 1 nanosecond. It is time distribution for currents of explosive emission. It is time distribution for current. It is time distribution for aluminum. It is 2 nanoseconds. Next slide, please. The plasma expands adiabatically since it gets the bulk of energy at the cathode is a very short time. In this case, the velocity of plasma expansion is defined by the equation. Plasma velocity, the sublimation energy over heat factor, and energy delivered to an atom of cathode metal, epsilon. It follows that the plasma expands right from the start in the form of heavily ionized plasma. This demands for every atom to get the energy. Epsilon sub P is the initial plasma energy. Energy sub E is the ionization energy. Epsilon sub C is the sublimation energy. For tungsten, energy of plasma about is our experiments about 60 electron volts. Energy ionization 8 electron volts, and energy sublimation more than 8 electron volts. Thus, the total energy epsilon is approximately equal to 18 electron volts. Next slide, please. This slide listed in table are experimental values of the velocity. It is metal and sublimation energy. It's cathode flare expansion velocity. Velocity is over heat factor. Next slide, please. The plasma is very inhomogeneous in density. Near the cathode, up to a distance of about 100 micrometers, the density of the plasma is of order 10 to the 20s per cubic centimeter, and further falls along a radius. The electric temperature of the plasma at the cathode is about 4 to 5 electron volts. It should be noted that the plasma properties are closely associated with the discharge current. The discharge current, until one cannot flare occurs, is an electron current of explosive emission. After the occurrence of the anode flare, there occurs an ion component on the current from anode. There are three types of the discharge current, namely a steady regime, unsteady regime, and saturation 1. Besides, if the discharge current in the saturation regime is small, it cuts off. Next slide, please. In the stage of steady emission, the discharge current is defined by the Chandler-Muir law as follows. It's Chandler-Muir law for a spark stage of vacuum discharge current and voltage, and it's constant. Phi is function of ratio, this ratio V plasma expansion velocity, gap, and T time. Next slide, please. For a circuit with resistance R, it's our case, a voltage voltage, the dependence of current and time can be determined from this equation. Discharge socket nanosecond pulse generator. It is a rise current. In our experiment, electric field 1 million volts per centimeter, and velocity of plasma million centimeter per second, and this air at 2 wave resistance 100 ohms, and hence the current rise 10 milliard ampere per second. As this data good agreement with experiment. From the formula, this formula, that for the commutation time defined approximately as d divided by v. This formula, the time commutation is proportional d, as the same good agreement as good agreement with experiment 2. These data are in a good agreement with experiment. At low discharge current of order 1 to 10 amperes and low current densities order 1 to 10 amperes per square centimeter, the electron current and the current of plasma become equal to each other. Of this case, the pressure of plasma and that of electric field are equal to each other too. This results in deceleration of the current rise. Such a regime is called the saturation 1. The unsteady regime of discharge current comes at high densities of the discharge current being in excess of 100 amperes per square centimeter. During this regime, chaotic current spikes with a duration of a few nanoseconds occur. The current density on the beam axis increases and the plasma potential on the edge of the cathode plasma becomes as high as several kilovolts. Detailed explanation of this effect exceeds the limit of our report. Now we pass over to the consideration of the question about craters on the cathode. After explosions, a number of craters forms on the cathode. The crater radius increases at a velocity of order 100,000 centimeters per second. The density of the current through the distraction zone during a few nanoseconds after the explosion is more than 100 million ampere per square centimeter. And next slide, please. And decreases. Oh, not so good. It is a function phi. It's for function phi for point cathode, plane cathode, and both point and plane cathode, and this condition. Next slide, please. It is a crater on the copper cathode formed as a result of flowing 20 nanosecond, 20 ampere explosive emission current. And the craters commonly occur as soon as in a few nanoseconds. We observed craters after 5 nanoseconds. Before 5 nanoseconds, we don't look crater. Occurring on the crater rims are micropoints with a field enhancement factor up to 50. Next slide, please. It is a dependence between factor B field enhancement factor as a function of pulse duration for molybdenum cathode. The factor B, this factor after discharge, after discharge with short pulse, this micropoints appearance as a result of this explosive emission. At a pulse length of order 1 nanosecond and shorter, the occurrence of micropoints stops. The cathode erosion results in the formation of micro drops. The most probable micro drops size ranges 0.1 micrometer. It is usual diameter of micro drop, 10 to the minus 5 power centimeter. Next slide, please. Focus, please. This slide shows the mechanism of formation of the craters. No. It is micropoint and field emission, and after several nanosecond explosive and appearance of plasma, and the liquid phase. It is microdrop and plasma expression, and microdrop and appearance a new micro protrusions with factor beta more than 10 between 10 and 100 and 100. We have carried out the numerical simulation of the cathode processes in the emission side. The model included such processes as, next slide please, as transfer by conduction and by convection, Joule energy release, and expenditure of energy for evaporation and melting. In the energy balance of the cathode surface, the processes of electron emission and bombardment by the ion from the pre-cathodic zone were taken into account. The calculation have shown that the processes of energy release in the cathode spot is dominated by a Joule volume heat source. The contribution of ion bombardment to the energy balance is very small. The electron emission was calculated by the formula of Richardson-Schottky. The cathode temperature in the emission side zone is typically of a few 10,000 of kelvins. The emission side lifetime is defined by the cooling of the cathode in the emission zone. This calculation you can see in proceeding Litvinov and Parfenov report. An important process on cathode erosion is the formation of new emission sites under the plasma. Experiments were carried out with the use of a wire probe moved to the primary cathode flare. This experiment, anode, cathode, wire probe at distance L between trigger electrode and probe. It is a dependence between ion current density and distance between this cathode and this probe. Experiments in a time after the occurrence of the cathode plasma exceeding the ratio L, this ratio L over V, a current was initiated in the probe circuit and spectral lines of the ions of the probe material appeared. At rates of current rise from 10 to the 8 to the 10 to the 9 ampere per second. Three typical regions were revolved. Next slide. Three typical before. Three typical regions of appearance of new craters. 1, 2, 3. And this region, the possibility of appearance of new crater is more. And in this region, we don't observe a new crater. There are two possibilities for the formation of new emission sites under the plasma. The first one is an explosive point in the field of the ion volume discharge at cathode. The second one is a breakdown of dielectric films and inclusions after charging them by the plasma ion current. The electric field that causes the explosion of point can be available only in the limits of few micron radius from the center of the initial explosions. Therefore, the most probable is the second mechanism for the emission site formation in region 1 and 3. In region 1, the fast charging of inclusions, the electric inclusions and the electric films occurs due to a high ion density. In region 3, this is associated with a great velocity of ions at potential bars on the cathode flare edge. The next slide shows the mechanism of the formation of the mechanism of the formation new emission sites on the cathode after a breakdown of the electric field at the cathode. It is a plasma, ion current, and micro protrusions, and field emissions, these micro protrusions, and breakdown of this this dielectric film, and appearance a new crater. Next slide, please. Let us consider now the relationship between the cathode spot of a vacuum arc and the emission sites associated with explosive emission. These phenomena have a number of common characteristic features. Beginning from the 1968, we were keeping to the statement that the emission site is a cathode spot. This, we were keeping to the statement that the emission site is a cathode spot. As emission science and cathode spot is the nature of this phenomena is the same. This concept was used in some models of the cathode spot by Mitterauer, Dalder, Hanche, Jutner, and others. The significant part in the development of these ideas was played the work by Fourchet and Vorontsov-Veliminov. There are two kinds of the cathode spot: the mobile cathode spot and the unmobile one. The random motion of the first kind cathode spot can be explained in terms of the formation of emission sites under the plasma by charging the electric films on the cathode. The distance between any two cathode spots is about 10 of microns. This is close to the length of region 1, where the occurrence of emission sites is probable. The next slide. Trace of the first type cathode spot moved in a transverse magnetic field. It is by Uttner along the oxidized molybdenum cathode surface. Next slide, please. Moreover, the first kind spot form of the ill-cleaned cathode surface only, while that of the second kind occur on the surface conditioned by discharge. The first kind spot operates due to micro explosions of the point that have formed during the previous occurrence of explosive emission. Next slide, please. No, before. Return, please. Oh, I see. It is a trace of the second type cathode spot moved slowly along the copper cathode surface for 5 microseconds and 100 ampere current. And many craters, and it is a slight trace of the second type cathode spot moved in a transfer magnetic field along the pure molybdenum cathode surface with current 30 ampere. It is slide Uttner slide, Uttner photo. This deduction was made by us in Tomsk and by Uttner in Berlin. 1 minute, I need. Our investigation, our investigation on cathode processes enabled us to carry out the detailed comparison between the principal properties of the cathode spot and that of the emission side of explosive emission. We compared the following characteristic: the rate of cathode erosion, the temperature and the density of the plasma at cathode, the velocity of cathode plasma expansion, the current density from emission side and cathode spot, the current cutoff, the availability of microdrops and microcraters, and so on. The comparison has indicated that these phenomena are analogous to each other. Therefore, we consider the explosion on the cathode to be an elemental act of operation of the vacuum arc cathode spot. Thank you very much. I ask Dr. Uttner help me because my English is not so good.
Questions for the speaker?
Yes.
In your numerical simulations or in your experiments, did you ever notice the existence, after you put the voltage pulse onto your anode-cathode system, did you ever notice in the interelectrode region the formation of a voltage maximum, in the sense that you have a peak